Good afternoon, and welcome to this webinar on aluminium design with SCIA Engineer. Today, I would like to tell you something about aluminium and the design of aluminium structures with our software SCIA Engineer. My name is Björn van den Steenam, and I work as Customer Success Team Lead at SCIA. During this presentation, the attendee audio is muted. You can use the questions box to ask questions during the presentation. After my presentation, I will have a look at the questions and try to provide an answer to them. This webinar will be recorded and posted on the SCIA by Alplan YouTube channel within a few days. As introduction, I will talk about the use of aluminium and its advantages. I will show some applications and indicate why SCIA Engineer is a good solution for your aluminium design. After that, we will have a look at aluminium cross-sections and their classification. I will illustrate how to create, use, and manage your cross-sections within the software. And finally, we can discuss which types of structural analysis are possible and how to perform the design and checks. On the right side, you can see a picture of an aluminium dome in Italy. This structure was built some years ago, but in fact, people started using aluminium already in the beginning of the 20th century to build some extraordinary structures. One of those structures were the so-called airships. The most famous example was the Zeppelin. Later on, in 1958, another extraordinary structure was the Atomium in Brussels, where aluminium was used for the cladding. But why would we use aluminium for structural design? There are three important benefits: lightness, corrosion resistance, and functionality. First of all, aluminium has a low specific weight, which is about 1/3 of the weight of steel. Some advantages of this are simplification of the assembly phases and the possibility to transport fully prefabricated components. Structures can also be dismantled easier, which leads to circularity and thus sustainability. Secondly, aluminium also has a good corrosion resistance due to the formation of some kind of protective oxide film on the surface. This leads to a reduction of the maintenance costs, and it provides a good performance in corrosive environments. Due to the extrusion process, there is a big freedom concerning functionality. Here you see some dimensions of an extrusion press. And within the limits of the extrusion press, you have quite some flexibility for the shape of your cross-section. This means that you can optimize the geometrical properties of the cross-section by designing a shape which simultaneously gives the minimum weight and the highest structural efficiency. For example, instead of using a regular eye section, you can add some stiffeners, lips, or bulbs to strengthen the cross-section or to reduce local buckling effects on the location where it's needed. Or, as you can see in the last cross-section at the bottom, you can add some triangular part to increase the torsional resistance of the section. Extruded sections can make it also possible to use easier connecting systems. For instance, by clicking instead of welding or bolting, and thus improving your joint details. Let's have a look at an example of a simple supported beam. When using an IPE 240 cross-section of steel quality S355, we can obtain a deflection of around 12.3 millimeters, a unity check for bending about a strong axis of 0.56, and a weight of around 31 kilogram per meter. When we take an aluminium section, which leads to a similar unity check, our weight has dropped to 12.2 kilogram per meters, but the deflection is a bit higher than for the steel section. Now, let's use the advantage of the flexibility of the aluminium material, and we can add lips of around 50 millimeters. This will lead to the same deflection as for the steel section, a lower unity check, and we are only at around 55% of the weight of the steel section. So we could use aluminium for applications such as temporary structures that cannot weigh too much, and we will obtain the same capacity with only 50% of the weight of steel. When we look at some applications, we could split them roughly into two big groups. The first group would be the lightweight structures or secondary structures. And there some applications are the light wall systems or facades, the balustrades, walkways, scaffolds, or supports or portals, for example, for traffic signs. Next to that, we also have the load-bearing structures. Think about long span roof systems in which live loads are small in comparison to the dead loads. For example, our domes that we saw earlier, or large span areas and auditoriums. In Belgium, aluminium was already used in 1964 to create a span of 67 meters for the roof of the Velodrome Kuipke in Ghent, as you can see here on the right side. Other fields are corrosive or humid environments, such as bridges or offshore platforms, industrial hulls, masts, helicopter decks, and many more. For your aluminium design, SCIA Engineer offers a good solution. First of all, the software can calculate the characteristics for any cross-section and determine the classification of the cross-section. It's also possible to personalize the profile library in order to work with specific cross-sections that you need for your projects. Various types of analysis are available, starting from a linear and a nonlinear calculation to more advanced analysis types, such as stability analysis to determine the buckling shapes, or even dynamic analysis to calculate eigenfrequencies, seismic analysis, or vibration analysis. After the analysis, the internal forces can be used to perform Eurocode 9 verifications. A detailed output will be available to illustrate how the unity checks are derived from the internal forces. And with this detailed output, you can also show the formulas from the code. Those can be printed, as well as references to the formulas and the articles from the code. At the moment, the current Eurocode 9 is implemented. This code was already published in 2007, including some addendums of 2009 and 2013. Currently, the second generation of Eurocodes is on its way. Next year, the final text should be available in order to publish in 2027 and to have the withdrawal of the current Eurocodes in 2028. SCIA is following up closely on this topic and will implement this new generation in the software, as we did for the first generation of the Eurocodes. A second topic that we will discuss is the cross-sections, which is an important topic and which will also lead to the classification. The calculation of aluminium starts with the design of the cross-sections. In SCIA Engineer, you can start from a parameterized cross-section. For example, when you want to use a rectangular hollow section, or you can create your own specific shape via the cross-section editor. In the editor, you can freely create a desired shape, or you can import a shape from a DWG or DXF file. In that case, two representations are present. The exact basic shape, which includes all stiffening elements, corners, notches, and this one is used for the calculation of the cross-section properties, such as the area, the moment of inertia, and critical for lateral torsional buckling. On the other side, there is a simplified tin-walled representation. And that representation is used for an automatic classification of the cross-section and the calculation of the effective section. Of course, you can consult the classification and effective section already before running an analysis to get an idea how effective the cross-section will be. As you can see on this slide, we have four classes. For classes 1 and 2, we can count on plastic capacity. So this will lead to the highest cross-section properties. A cross-section of class 3 is considered elastic, which means that the full plastic moment resistance cannot be accounted for due to local buckling. For class 4, cross-sections local buckling effects will reduce further your effective properties that can be used for the check of the cross-section. This is to illustrate that classification is important. The benefit of extruded aluminium is that changes can still be made. So, in case of a class 4 classification, you can try to make changes to the section and check the effect on the classification and effective properties in order to arrive at a more beneficial class 3 or even higher. On this slide, the classification process is explained briefly. This is directly coming from the Eurocode, and it's automatically executed by the software. What is happening? The stresses are calculated, and the stress gradient is determined. This will lead to the calculation of the slenderness beta, and that slenderness is compared with limits from the code. And the limits depend on the type of part that we are considering. And that can be an internal part, a symmetrical outstand, an unsymmetrical outstand, and so on. Then the effective thickness is calculated based on several reduction factors. We have reduction factor for local buckling, we have one for distortional buckling, and we have the heat effective zone effects. And this is nicely indicated on the figure on the bottom left side, which is coming from the Eurocode. In the dialog of the initial shape, you can find the type of parts. So here on the slide, you can see we have plate types, part types UO, so unsymmetrical outstand, and I, that's internal parts. And you can also define the longitudinal welds. The effect of the welds is immediately taken into account in the classification and the effective section. It's also possible to reuse cross-sections to avoid that you have to create your cross-sections each time over and over again. One way is to create an empty template project in which you predefine the cross-sections that you regularly use. Then you can start for your new projects each time from this template file. It's also possible to create a database file this database file can be loaded into your project file. And the third possibility, which can be used for standard cross-sections, is to edit our profile library. On the image on the right side, you can see some rectangular hollow sections with a specific radius for aluminium. Let's have a look at an example in SCIA Engineer. I will show you a simple facade with some specific cross-sections for the horizontal rails and the vertical mullions. So, if we open our model in SCIA Engineer, we can see what we have modeled, so some horizontal rails and some vertical stiles. Let's start with the materials. So we can go to libraries, materials, and you can see here that we have a big list of materials predefined in the software. Now, often only a few qualities are used. So what you can do is simply select with the Shift button multiple materials and delete those until you only keep the materials that you regularly use. If you would need later on one of the materials that you have deleted, you can always use this button, read from the system database, and then you can import the quality from our library database. So this can lead or will help you in having a better overview with all the materials that you regularly need. Then we can have a look at the cross sections. If I create a new cross section, you will see some groups. First group is the profile library. There you have quite some different shapes with different subgroups. For example, here we see the HA sections or IPE sections. You have the tubes. Know that here those are predefined values, so you cannot modify them, and they have predefined radiuses, which can differ from the ones that you are used from aluminium. Therefore, you can create your own sections. We have here a group tin-walled geometric, which are parameterized shapes, an I shape, a hollow section, rectangular hollow section, and in those groups you can apply your own dimensions. So let's assume something like this. And then with one click on the button, you can update and you immediately get the characteristics calculated. We'll cancel. And then when you have extruded cross sections, you could go to the general group. And then we arrive in the cross-section editor, where you can freely draw your cross-section with polygons and polygonal openings. Or when you have already a cross-section, you can import it from a DWG or DXF file. I have here an example. I can select the polygons, so that will be my outer line. I can select polygonal openings, so those are these openings in the section. And then I can import the selection. I can select or define a material. These are the openings. And I put my cross section somewhere in this zone. This is the exact shape, so all the lips and notches and so on will be taken into account for the calculation of your area, moment of inertia, and so on. For the classification, we would need a tin-walled representation. When I select it, we are asked for material again, but here we are now obliged to give a thickness, for example, 3 millimeters, and then you can define your shape. So I will do it roughly just to give you an example, like this. If this has a bigger thickness, you can do it again, for instance, with 5 millimeters for that part. And then here at the other side, you will make some simplifications. So for example, I take again 3 millimeters, and you don't need to define every lip or every notch, but you can simply define the big parts which are relevant, for instance, like this. And then when you're finished, you can close, and we have this cross-section in our model. When you press update, then we get the cross-section characteristics, the gross cross-section characteristics, so your area, moment of inertia, and so on. And we now have as well an initial shape available. You can see it's with the shape, the Tynwald representation, and you can define the types for your parts. And those will be taken into account for your classification. Let's have a look at one of the cross-sections that was already in this model. So this is the cross-section. Let's go to the properties, the initial shape. So we can see parts 1, 2, 3, 4 are internal parts, and then the others are unsymmetrical outstands. When we go to the classification, we can see when this cross-section would be purely on compression or purely on bending my plus, and so on, how it will be classified. Of course, later on, after the analysis, the exact internal forces will be used for your classification. This is preliminary, that you can get an idea when it's on a certain force. So let's take bending My, and then we see here, for example, part 1 is classified as class 4. This part 1, and also part 2, when we look to the negative side, part 2 will be class 4. Those have, in this example, a thickness of 3 millimeters. With the class 4, we also get our effective characteristics, and we see, for example, for moment of inertia y, 7.27 to the e minus 7. Let's have a look at the other cross section. So you could make the evaluation and see, okay, I don't have an I don't have a fully efficient section. I could increase the thickness of some parts. And that's what we did here. We made a Tynwald representation with a bigger thickness for parts 1 and 2. Now they have a thickness, you can see it also here visually, of 5 millimeters. And this leads us to a class 3, which will be elastic, which you can see as well in the characteristics, because now my effective properties have increased. I have now 1.25 e to the minus 6. We will have a look at the effect in the check as well. Now, when you work with the standard cross sections, we saw that we can create them with the parameterized group. We can also implement them directly in the library of the software via editing the profile library. In that case, I could add a new type. Let's call it LUK. It's a rectangular cross section, hollow section. Okay. And now I am in the profile library editor. And here I can create my sections, LUK, let's say 5053, and add the dimensions. Or delete it. If you have already a list, you can simply copy and paste the list. Now, pay attention when you save this, you get a warning that you need the area and the inertia IY. This is just how the software works. So what you can do is simply take those columns into account as well and define a unit value, because later on the software will calculate it automatically. So I will remove everything and I paste, including now the area, just a unit value. I can save it. And now when you go to the cross sections and you create a new one, you can go to the profile library, to your rectangular hollow sections, and our subgroup is created. You can go to one section, and you see immediately it's not the unit value that you see here, but immediately the calculated value from the software. All right. So what do we have as well? We have our cross sections, we have the structure. We can have a look at the loadings. I activate the layer of the panels, and you can see that I have used load panels, which is some kind of entity which will redistribute the loads. What does it mean? If I go to the view settings, I can highlight or display the tributary areas. So it means that these areas will indicate how the load will be transferred to your 1D members. So if we would apply here the surface loads, small load 001, when the loads will be generated prior to the analysis, they will be generated as line loads on your 1D members. So that is quite useful because it's nice to work with surface loads, and with the tributary areas of your load panels, it will be automatically redistributed to the 1D members behind it. I will disable the panels again like this. The model has already calculated, otherwise you can use the calculate button, and we can have a look at some results. For example, the 3D deformations. I have created an SLS combination, and I see some deformation in the horizontal rails and the vertical mullions. You can ask for the internal forces. For instance, when you ask for the bending moments, you can evaluate or have a look where the zero moment is located. Of course, the position of that zero moment can differ if you have multiple combinations. And you can go to the Aluminium sub workstation. And there we have the SLS check. So for checking the relative deformations, you can refresh, and we see here a unity check of 0.44. So it satisfies the check. It will compare the relative deformation from the structure with a predefined limit from the aluminium settings. And then we can have a look at the ULS check. Let's take, for example, this vertical element, 0.17, and we can open the detailed output with tables and formulas. And we can see here that with these internal forces, we have a class 4. and we have a shape factor of 0.79, and the unity check for the bending moment 0.17. If we now go to the structure on the right side, which is the same structure, but we use the cross-section with class 3, so with a bigger thickness, the unity check lowers a bit, 0.15, so we have increased our capacity, which you can see in the output as well. We still have here a bending moment MY classification class 4, but that's due to the outstands, so those will have a limited influence. And you can see that as well in the shape factor, because that one increased until 0.93, which leads us to a lower unity check. Let's go back to our presentation. On this slide, you can see the load panels to simulate the trapezoidal distribution of our loads. This was also tested in the University of Ghent, and there they saw the same behavior and the same distribution coming from the areas, the tributary areas that the software indicates, and that you can also see here in the middle picture. We also had a look at the deformations and the internal forces. I have one additional remark about the boundary conditions, and that is that SCIA Engineer assumes the connections by default as fixed when you don't add hinges to the model. In this model, we have added hinges on the horizontal rails. And for the stiles or the vertical mullions, you can have a look at the zero moment point, as we did in the internal forces. And often a tube with a certain length is inserted at that location. In the software, this could be modeled by creating an additional cross-section with a tube inside the mullion. So in the cross-sections, you can choose again for the general cross-section. We already imported the shape, the specific shape of that mullion, and you can add an additional tube inside that shape. And on the right side of the slide, you can see the unity check, the ULS check, with the output, including formulas and references. For the last part of the webinar, I will tell a bit more about the analysis types and the checks in SCIA Engineer. The most simple analysis is a linear analysis. This analysis will calculate the load cases separately, and when asking for a certain result of a combination, the software uses the superposition principle of our load cases to derive the combined result. Via stability analysis, you can determine the critical load factor or alpha critical factor to check if you're allowed to perform a first order analysis or if you need to take into account additional second order effects. A stability analysis can also give you a better insight in the behavior of the structure, especially related to buckling effects, as you can see here on the right image. In case that you have non-linearities in your model, such as members that only work on tension or supports that work differently under tension and compression, you need to create nonlinear combinations and perform a nonlinear analysis. It's also possible, and sometimes mandatory, to perform a more accurate analysis and calculate with second-order effects and imperfections. For the imperfections, you can define a fixed value, or you can let SCIA Engineer calculate the imperfection value with formulas from the code, or even apply the buckling shape as an imperfection coming from the stability analysis. Also, dynamic effects can be taken into account in the analysis. It's, for instance, possible to calculate the eigenfrequencies of the structure. For bridges, this is relevant to evaluate if vibration effects should be considered or not. For regions where seismic activities can occur, a seismic analysis can be performed. When you obtain the deformations and internal forces after the finite element analysis of the full model, you can perform the necessary checks. Due to the lower elastic modulus, often the SLS design is decisive. In SCIA Engineer, you can define the deflection limits in the aluminium settings or in the buckling settings of the 1D members, and these limits can be compared with the relative deformations of the structure. Then the ULS checks can be performed. Both section checks as stability checks are executed. As you can see here, the individual checks like tension, compression, and so on, including the effects of longitudinal and transverse welds. As we saw in our first example, we can obtain a detailed output with formulas, with references, so you can clearly follow the checks starting from the internal forces until the final overall unity check. In our web help, help.scia.net, several benchmarks are available. Let's have a look at a second example in SCIA Engineer. This example concerns the design of an aluminium bicycle bridge. The cross-sections were designed starting from the connections, and for the bridge deck, an extrusion plate was used that is also used for helicopter platforms. The span of this bridge is around 40 meters. So let's have a look at this model in SCIA Engineer. This is the 3D model with the volumes. We can have a quick look at the cross sections. We can see there are several aluminium cross sections used for the bracings, for the deck beams, and so on. We have loaded the bridge, and now we can have a look at some analysis types. We executed a linear analysis, so we created some linear combinations, and now we can execute the linear stability analysis to find out what our alpha critical values are and how the buckling modes behave. So let's go to the linear stability combinations, where we can convert our linear combinations into stability combinations. You have a button for that, new from linear combinations, so you don't need to create those manually over and over. Then after executing the analysis, we can go to the results. First of all, you can have a look at the critical load coefficients, so the alpha critical values. And here we get a list of our combinations, so around 22 in total. And for each combination, we asked to calculate 5 modes. And we can see in the table that, for example, for mode SL4, we have our first mode with an alpha critical value of 9.3. So since this value is smaller than 10, you should use a second order analysis with imperfections. We can also have a look at the mode. So we go to 3D deformations. The type of load is the linear stability combination. And then we get the same list of modes and combinations. So we can opt for the fourth combination and the first mode. Pay attention to activate wireframe in order to have a quick visualization of the results. And then we can see that we have the upper chord, which is buckling out of plane. The value here It doesn't have a physical meaning. It's a normalized result. It's normalized to be able to show the mode visually. Now we can apply this as an imperfection. So we can go back to the loads, and there we have an option to define global imperfections. And here the first one is a global imperfection based on the buckling shape of a linear stability combination. Combination is number 4, the first mode. And now we need to define a maximum deformation value because the mode itself, it's a normalized result. So now we need to define a physical value for the maximum of that mode. So you can calculate this with the Eurocode. There you will find a table which indicates, depending on the kind of buckling mode, what the ratio in comparison with the span should be. For example, L divided by 200, and then you can calculate that value. And we can do it once in a positive direction, once in a negative direction, and if needed for multiple modes. And then in the nonlinear combination, you can apply that mode and that imperfection. For example, here, this one has a specific content, and there you define the global imperfection. If you define a global imperfection based on the buckling shape, you don't need to combine it with a bow imperfection, because then you're applying two imperfections, which isn't needed. And then you could go to the nonlinear analysis, execute the analysis, and go to the checks. Let's go to the ULS check for the nonlinear class. Refresh. Then you can see here the maximal check is in that upper court. If you go to the detailed output with the formulas, and then open the report preview, you get to see all the details, so all the section checks, and after that the stability checks. And in the stability check you can see flexural buckling isn't executed because we are calculating with second order, including imperfections. And therefore we have activated in the aluminium settings this setting that the flexural buckling is taken into account by second order analysis. All right, another analysis possibility is a dynamic analysis. So this is a footbridge, or a bicycle bridge. So we could check the vibrations if they should be calculated and checked or not. Therefore, we can create masses, because a dynamic analysis needs masses, and mass groups. So similar to combinations, we now have a combination of mass groups. I have created two combinations, one with only the self-weight, one with self-weight and variable load. After that, we execute the modal analysis, and then we can go to the results, and we can have a look at the calculation protocol for the eigenfrequencies. This is the first combination of mass groups, and we see here we calculated 10 modes. You can see the frequencies. So depending on the frequency, you can check it with the code, like for example the Citra guide, and you can check if you should check the vibrations or not. You can see here in the columns after that, for example the fourth mode is a vertical mode, because here you have a big coefficient. You can also visualize it. You see it here as well in the column WZ divided by W total, 0.768. So that's almost 77% that is vibrating vertically. So that's the biggest mode vertically. Also, this can be visualized. So if we go to type of load, mass combinations, and we go to the first one and the fourth mode of that first combination, refresh, and we can clearly see the vertical modes. What I didn't show you just before was the imperfection. Also that can be visualized. So if we go here to SL4+, then we see the same mode from our stability analysis, but now instead of the normalized result, we have the maximal value that we defined in the imperfection itself. So we saw in the software that we can ask for the stability modes and the critical coefficients after we executed the stability analysis. Then the stability mode was applied as an imperfection, which can also be visualized via the 3D deformations. In the nonlinear analysis, we took into account the imperfections and the second order effects. And after that, you can use the nonlinear combinations to perform your SLS and ULS checks. We also executed the modal analysis. The first table indicates, let's you evaluate the different modes with their frequency and their participation. And then the mode can also be visualized with the 3D deformations to get a better insight in the behavior of the structure. Finally, all input data and results can be shown in the engineering reports. You can add multiple images in an automated way, for example, to show the loads. In that case, you can add the load cases item and indent a picture under that item. And as a result, you will get a picture for each load case that is present. It's also possible to add drawings of the model in the report. Those could be generated automatically when you use a 3D line grid. And you can customize the report to your specific needs. You can change the picture, the logo of your company. You can add random text, and you can change the fonts and so on. And when you save the report as a template, it can be reused for future projects. So in that case, all the items that you have added in the navigator will be present in your new project. And when you regenerate the report, the items, so the tables and the pictures will be updated according to the new projects. This brings us to the end of our webinar. I already want to thank you for your attention and would like to explicitly thank Cyril Klauwaert for his valuable input for this webinar. Thank you for your attention.